So, we're reached the final part of the module. We're going to talk about optimal emission reduction. And today I'm going to talk about three things: international agreement on targets. I'm going to talk about cost-benefit analysis, and I'm going to talk about co-benefits. And this is where we are in the sequence. We are in the final 3 weeks. We talk about where emissions come from and what you could do to reduce emissions and what that would cost. We talked about why climate change is a problem, and now we're going to bring it together in a cost-benefit analysis. So this week we're going to do the politics as well as the first best. Then next week I'll be on strike. The week after we're going to talk about the strikes again. The week after we're going to talk about uncertainty, equity, and time discounting. And then the final week we're going to talk about international environmental agreements, and this will be cut short to 1 week rather than 2. And what we're going to drop are acidification and the hole in the ozone layer. So we're not going to skimp on climate. In the final seminar, instead of discussing the homework that comes with this, we're going to talk about the exam, right? I have now written the exam.
Is it a hard one? Or is it weird?
I never think that my exams are hard, but students always disagree. So I think it's perfectly doable, but we'll talk about it later. Today we're going to talk about optimal emission reduction, and rather than start with the economics, I'm going to start with the politics and the physics of this. So Article 2 of the United Nations Framework Convention on Climate Change, agreed in 1992, says that the ultimate objective of this convention is to achieve stabilization of greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Such a level should be achieved within a time frame sufficient to allow ecosystems to adapt naturally, to ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. So this is language from 1992, and it is very hard to disagree with this. We don't want to do dangerous things, I guess we all agree, and it's not just any danger that we're talking about, but it is actually specified in the second sentence. We should allow ecosystems to adapt naturally, and we would ensure that food production is not threatened. And those seem very laudable aims, and that is one of the reasons that the vast majority of countries signed up to this convention within a few years. It was negotiated in 1992 and entered into force in 1995. But the question really is, what does this mean? And does it mean anything? And let's look, we can all agree that we want to avoid danger, but that is undefined. Natural adaptation or adaptation of ecosystems, what does that mean, right? And what sort of climate does that preclude? Well, what you're looking at here is the end of the last ice age, the Younger Dryas, when we saw very rapid we saw very rapid cooling and very rapid warming. With geophysicists, you never know what the scale is like, but this is indeed cooling, and this is cooling, and this is indeed warming. And this is only 8,000 years ago. No, it's a bit more. It's about 12,000 years ago, and this happened naturally. There's no reason to assume that the ice ages started or ended because of human interference. And what happened here was that Lake Agassiz broke or ended. So because of all the meltwater of the glaciers melting at the end of the ice age, an enormous lake was created in what is now Canada, and then at one point, and that was sort of propped up by an ice dam, and at one point the ice dam broke, and that lake, which is a big lake, it's about 5 times as large as the big lakes are today, all that water was dumped into the North Atlantic, and that sort of completely messed up ocean currents, and that explained the very rapid cooling and then the very rapid warming after that. This all happened for natural causes. Ecosystems made this through it, right? So, and the warming and the cooling that we see here is much, much more rapid than anything we would expect. I mean, we're talking about 15 degrees of warming. This does not pose any constraint on climate change. There's nothing in the future of anthropogenic climate change as dramatic as the younger dryas period. So this does not impose much of a constraint. Food production not being threatened. That's also a good thing. You all like to eat, right? Or even if you don't like it, we all have to eat. But the threat is not specified. It doesn't say whether the threat comes from climate change or from climate policy. This is a piece of work that was published in, I believe, Science, but it may have been Nature a while ago. And it's looking at the future of the energy system. And in this particular panel, there is very little climate policy. And in the other 3 panels, there is a lot of climate policy. And this actually only gets us to the upper end of the Paris Agreement, of the targets of the Paris Agreement. And what you see is that one way to get there, maybe the only way to get there, is by sucking CO2 out of the atmosphere and to use negative carbon energy. And we talked about that before. What you do is you grow trees that suck CO2 out of the atmosphere, then you chunk those trees into what used to be a coal-fired or a gas-fired power plant. And instead of releasing the CO2 back into the atmosphere, you capture it and store it. And then you have negative carbon energy. You on net remove CO2 from the atmosphere. But to do that, to make a real dent in emissions, what you need is a lot of bioenergy crops. And here you see the acreates. And what you see is that in this particular scenario, 60% of the world's surface should be of the Earth surface, not the world, right? And we leave the seas alone, needs to be planted with bioenergy crops. It's very hard to imagine to do this without in any way threatening definitely it's a big threat to nature, but without driving up the price of food, right? And we've seen that one of the things that the Bush administration did is that there's a big bioethanol program in the US, which essentially pays farmers for growing maize, but instead of using that maize to make tortillas, that maize is diverted into biofuels. And that's, I believe, a third of the crop is now diverted to that. And that obviously drives up the price of tortillas. And what you're looking at here are protests in Mexico against the price of food. So this Article 2 seems meaningless in the sense that it doesn't really impose any guidance on climate policy. And anybody can agree to this, and everybody agreed to this, but that's because there is no real substance here. Go ahead.
Well, hasn't it been like 20 years? It's been 20 years since that was done, as much.
30. Yeah. It's 30 years ago, 1992. So this seems innocent, right? In the sense that it doesn't impose any constraints on our economies or our policies. That is not true. And the reason that it's not true hinges on this particular word, stabilization. So what does that mean? Let's go back to the carbon cycle. So let's assume that the carbon cycle is governed by a first order linear difference equation. So the concentration at time t depends on the concentration in the previous period, and part of it, only a fraction of it remains. And of course we also add emissions to, and you know this equation because you worked with it, right? So what does stabilization mean? Stabilization means that the concentration doesn't change, or that mt is equal to mt minus 1 for all t, right? Or another way of doing this is that you drop the subscripts from your equation, and you have m is delta m plus e, or m is e over 1 minus delta. So if this is true, then stabilization of concentrations means that you need to stabilize your emissions. And once you've done that, you're done. So suggest that there's no guidance whatsoever in the United Nations Framework Convention. But that is wrong. We looked at a version of this cartoon before. Talked about all the fluxes of CO2, all the stocks of CO2. These are the fossil fuel stocks in the atmosphere, and then the fluxes. And we talked about how big these fluxes were, and that terrestrial exchange is much bigger than the annual emissions, and the ocean exchange is much bigger than the annual emissions. But a big difference between those things is that we only emit from the fossil fuel stock, whereas the terrestrial biosphere, yes, in autumn dumps a lot of CO2 into the atmosphere as plants die back, but then in spring actually sucks out, and summer sucks out a lot of CO2 from the atmosphere, right? And this CO2 flux from fossil fuels is not balanced by any uptake. So we talked about this. What I did not talk about was this particular arrow here. And the reason you may have thought at the time that I did not talk about this, because this number is so very small, 0.2 versus 120, right? So why talk about this? So this process here is the weathering of rock. And rocks are exposed to the atmosphere, and certain types of stone chemically react with the CO2 into the atmosphere, and rocks grow as a result, right? They take carbon out of the atmosphere, and rocks become larger. Now, as you may have noticed, rocks do not grow perceptibly. They do grow, but not particularly fast, and that is why this number is so very, very small. But what we've also done in the seminars is that we built a slightly more complicated carbon cycle model than the one that I just showed. And this process of removing CO2 from the atmosphere is actually crucial, and part of the CO2 is from the atmosphere is removed by rock weathering, and that is very, very slow. So really what you need to do is you can't assume that there is one atmospheric concentration of CO2. There's really 5 concentrations, and each is governed by its own first order difference equation, and that is the one that we implemented. And then what you also noted is that about 27%, if I'm not mistaken, of the CO2 in the atmosphere has a half-life, a characteristic half-life of 2 years. It means that after 2 years 50% is gone, and after 4 years 75% is gone, and after 8 years 87.5% is gone, right? That is how a characteristic half-life works. And then there's another fraction that has a characteristic half-life of 17 years and characteristic half-life of 47 years, and then there's also a bit of carbon that stays in the atmosphere for 363 years. And then there is the rock weathering, and this is about 13% of emissions, stays in the atmosphere practically forever.
Rock carbon. Rock carbon.
Yeah, well, it's removed at a geological timescale. So at a human timescale, it's not removed at all, right? So now we have a problem, right? Because we're talking about 1 minus delta, and delta is 1. So we're dividing by 0. That's always an issue. So we can't use this particular form, but we can solve this one, right? If m is delta m plus e and delta is 1, then there is a clear solution to this. M is m plus e must be 0. Right? So when people wrote into the United Nations Framework Convention in 1992, 30 years ago, that we should stabilize the greenhouse concentrations in the atmosphere, they essentially committed everybody to 0 CO2 emissions. They did not realize that at the time, and the people who signed up to this also did not realize what they signed up to. But since 1992, the goal of climate policy, internationally agreed, legally binding, has been to drive CO2 emissions to 0. Still, there is no agreement when we should hit 0. Should we hit 0 in 2030 or should we hit 0 in 2300, right? That is not contained in here. That is contained in the Paris Agreement, also in Article 2. It was negotiated 7 years ago in Paris, as you may have guessed. The United Nations Framework Convention was negotiated in Rio de Janeiro. And Article 2, 1a of the Paris Agreement says that this agreement aims to strengthen the global response to the threat of climate change by holding the increase in the global average temperature to well below 2 degrees above pre-industrial levels and pursuing efforts to limit the temperature increase to 1.5 degrees above pre-industrial levels, recognizing that this would significantly reduce the risks and impacts of climate change. So now we have a target, right? It's not just that we should drive emissions to 0, but we should drive emissions to 0 so that we hit the 2 degrees target and perhaps the 1.5 degrees target. That is what has been agreed internationally and has been adopted by most other countries. In the book there is a story about where the 2 degrees target comes from, which is a peculiar story, but we won't have time to go into that, and that's background information. I and many others think that these targets will not be met, and in the final week I have some more pictures of this. What you're looking at here are so-called committed emissions. We talked about how emissions are set in stone. That emissions come from the way your building is constructed. It comes from where you live relative to where you work or go to school. It comes from the lifetime, or it comes from the car that you drive and the machinery that you use to make electricity. Now, all of these things have a sort of an economic lifetime. Coal-fired power plants have a typical lifetime of 40 to 80 years. Gas-fired power plants, 25 to 40 years, and so on and so forth. So what they did in this particular picture is sort of say, well, this is the stuff that we have. This is their remaining lifetime. And if we assume that if everything at the end of the remaining lifetime is replaced by something that is carbon free, then these are the emissions, assuming that these things will continue their typical use. And there's a lot of assumptions in here, and there's by now 5 or 6 versions of this particular analysis. What you're looking at is, well, if we let things run out to the end of their economic lifetime, use them as they always have used, this is the emissions that come out. And this is existing stuff, and then in the light gray, you're looking at stuff that is currently being planned, or that in 2018 was being planned. And what you see is that the amount of CO2 that comes out is 850 billion tons of CO2. If you want to keep the temperature below 2 degrees, then we can emit another 1200 to 1500 tons of CO2. So that is doable, right? But if we want to keep the temperature below 1.5 degrees, then we can only emit 420 to 580 billion tons of CO2. That means that some of these things will have to retire prematurely, and some investors will lose their shares, right? Now, needless to say, analysis was done in 2018. We're now in 2022. A lot of what is here proposed actually has been realized, and more proposals are on the table, right? Including, because of the war in Ukraine, including going back to coal in Europe, right? Because we no longer want to import gas from Russia. So I don't think we're going to hit these targets, but this is what has been internationally agreed. So this picture here is the same as this picture here. Here it's done by an economic sector, transport, electricity, industry, and here it's done by country, right? So it's not just that people are going to lose their shirt, but investors are going to lose their shirt, but it's investors in India and China that are going to lose their shirt, right? That's where most of the commitment is. And India has already said, no way we're going to do this, right? China is a little bit of a different story because China is so autocratic. The government can essentially tell entire industries to go bankrupt, right? Although they would be hesitant to do that now, given all the trouble that they have in the property sector. Right, so that is where we are at the international stage. Let's look at what an economist would do with this. So we're going to do a bit of cost-benefit analysis. I'm going to go through the basics. I'm going to show you some orders of magnitude, and then we're going to look at Bill Nordhaus's DICE model very quickly. So, what do you do in a cost-benefit analysis? If you want to find an optimum, then you can do two things. Either you can set your marginal net gains to 0, or you can make sure that your marginal benefits of doing the activity equal the marginal costs of doing that activity. And you can do that as the benefits from emitting, or you can do it as the benefits from not emitting, right? It's just, right, do you read the graph from here to here, or do you read the graph from here to here, right? So how does this work? These are the marginal private gains from emissions, and of course there's no gains from emissions per se, but there's gains from the activity that emits stuff, like a warm home and a warm meal, right? Or transport. Those are your gains from emissions. If you do very little, those marginal gains are high, and if you do a whole lot of them, at a certain point you're not interested in using more energy, right? Because your house is warm enough, and heating it further would actually make you uncomfortably warm, right? And of course there's a cost to doing so. So at a certain point you stop using energy because it doesn't serve any additional purpose anymore. So this is where the unregulated emissions are. Then the higher the emissions, the higher the larger the environmental damages, or in this case the larger climate change. And what you want is, you want to stop at this point where the marginal benefits equal the marginal cost, or the net marginal, or the net benefits at the margin are equal to 0, right? So that is what you want to do in a cost-benefit analysis, equate the marginal cost to the marginal benefits. You can also do that algebraically. No, you can also do that in calculus, where we want to maximize our welfare. Welfare depends on our emissions, and we have the benefits of emission reduction and the costs of emission reduction. It's an unconstrained optimization, so we set the WDE equal to 0, which means the BDE minus the CDE should equal 0, or the marginal benefits should equal the marginal costs, right? This is just in calculus what I just showed you graphically. Now this holds for a static optimum, but of course climate change is a dynamic problem. It lasts for a very long time, so we can't just solve this as a static problem. Typically the way people formulate the decision problem about greenhouse gas emissions is to assume that climate change is a stock. It accumulates in the atmosphere, whereas emission reduction, the costs of emission reduction are a flow and only depend on today's action. This is not entirely how it works, but this is typically how it's done. And that means that the marginal costs are the marginal costs, whereas the marginal benefits are the net present value of the marginal benefits. Okay, so we want to maximize the net present value of net benefits, which by deciding at emissions and emission reduction at every point in time from E0 to E1 to E3 to E and so on and so forth. Now, as I said, the costs of emission reduction are assumed to only depend on your emission reduction in the same time. So nothing changes here, but now our benefits depends on what we did this year, what we did the year before that, and so on and so forth, right? And then of course we need to introduce the discount rate. Of the discount factor of 1 plus r to the power minus t. This can be okay. Now the marginal costs do not change much, right? It's still the CDE, but now this holds for period t, right? So we need to multiply it with the discount factor for period t. 1 over 1 plus r to the power t. The marginal benefits are first for s is 0, the marginal benefits in the same year, but then of course discounted again back to today with 1 plus r to the power t, right? Then for the year after, s is 1, the benefits of reducing emissions, the benefits tomorrow of reducing emissions today, right? That is what this term means at the margin. Then the benefits for the day after tomorrow for reducing emissions today, right? And then of course you need to discount that a little bit harder because it's in the future. So that is where this S comes from. And this is then the expression here, right? It is the benefits from that point onwards into the indefinite future. That is what the S does here. Now what you see here is 1 plus r to the power s plus t, which is of course equal to 1 plus r to the power s times 1 plus r to the power t. Now the t doesn't change, so you can bring that in front of the equation. And then we have 1 plus r to the power t here, and we have 1 plus r to the power t here. So that is good. And that drops out, and what we have is that the marginal costs of emission reduction at time t should equal the marginal benefits from that point t onwards into the indefinite future. And that is the term that you see displayed here. Now this looks more complicated and it looks more involved, but the principle is exactly the same, right? The marginal cost should equal the marginal benefits, and the key difference is that the marginal benefits are now a stream of marginal benefits into the future discounted to the point at which you make the decision, right? Now, what we've done in week 5, if I'm not mistaken, is we looked at this term here, and we called it a social cost of carbon, the marginal benefit of greenhouse gas emission reduction, or the marginal damage if you emit an additional ton. Go ahead.
So So I understand the maths. I'm just a bit confused why costs don't have any sort of discount function. Because surely there'll be like future costs to it as well.
This is essentially to make the math easier. What you could, of course, assume is that your cost of emission reduction today depends on your actions yesterday. And then you just have an additional term, or you have additional arguments here, and then this would become a sum as well. Strange, and you would think that is the way it works, because capital is long-lived and so on and so forth, and you would sort of say, well, that's how they stuck it in their models, but that's not what people do, really. But yeah, you can complicate this, and it doesn't change the inside at all. It just makes the math more complicated. So we looked at this term, we called it the social cost of carbon in week 3, and in week 5, and in week 3 we looked at the cost of greenhouse gas emission reduction, including the carbon tax that is needed to impose things, right? So we actually know these two numbers already. This is the marginal abatement cost, or the carbon tax, and this is the social cost of carbon. Now to start with this, I showed you a table. Here we have it in a graph. I also emphasized how uncertain this number was, so that is why you see confidence intervals here, but just focus on the median. And what I also said in week 3 is that the more stringent the target, the higher the carbon tax that you need, right? No surprises there. This is a logarithmic scale, so this is really an exponential curve, right? And what you see is that if you want to stabilize at 700, then a carbon tax today of $10 per ton of C is enough. But if you want to go to 450, then you need a carbon tax, well, let's pick 1,000. If you want to go to 425, then a carbon tax of $1,000 per ton of CO2, per ton of C is needed, right? That is how to read this particular graph. So you can sort of like see this as a supply curve, essentially. If this is the carbon tax you impose, this is the concentration you get. Or if this is the concentration you want, this is the carbon tax you need to impose, right? And this is the exact same information that we saw in that table. It's just now in a graph. We also looked at the social cost of carbon. Yeah, we did. And I summarized it here for a 3% pure rate of time preference. This is your social cost of carbon, right? This is if you have no climate policy, and this is the Baku tax if you have climate policy. What we found for a 3% pure rate of time preference, which is a reasonable number, you want to impose a carbon tax of around $25 per ton of C. Now, going back to this curve, what does $25 buy you? 650 parts per million. What did we say we wanted to do in Paris? 2 degrees target. We need to drive the carbon tax up to 500. 1.5 degrees, the carbon tax should be more than $1,000 per ton of C, right? And I actually have the word Paris Agreement there as well. So you immediately see the tension between what is politically agreed and what is optimal, right? Now, this is a rough and ready cost-benefit analysis where I simply said, well, the basic principle is that you equate marginal cost to marginal benefits, and this is what we find. Now, Bill Nordhaus, who won the Nobel Prize in 2018 for this work, did it all properly. Not sort of like, let's equate marginal cost to marginal benefits, but let's build a proper integrated assessment model. And it's actually very similar to the ones that you guys have been building. Very similar. Actually, the model that you've been building is in some ways slightly more complicated than what Nordhaus did. Not that you win a Nobel Prize for derivative work, right? So don't get your hopes up high. And essentially, it has all the feedbacks and all the bells and whistles in there, right? So rather than just equating marginal costs and benefits, we're properly optimizing net present utility. There's the feedbacks from climate change and economic growth are included, and so on and so forth. Also the feedback of reductions in emissions, the cost of that and the impacts on economic growth and emissions. All that is included, and that model, as I said, is very, very similar to the ones that you have been building. And the reason that he built this model was to answer the question, what is optimal climate policy? By how much should emissions be reduced? And you can kind of guess the answer by now. So Nordhaus assumed, or rather what comes out of this particular version of the model, there's many versions of the model. I think this is the 2005 version, or maybe the 2015 version. He imposes a carbon tax, right? Or rather, he calculates the optimal carbon tax. Previously, I said that's 25. Nordhaus actually starts at 40 and then lets it slope up by about 2% per year to roughly $200 per ton of carbon in the year 2100. And then he has a cost function. What will this buy us? Well, if you impose a carbon tax, you reduce emissions. As you can see, what we're actually looking at is concentrations, but the concentrations keep on going up, right? This is perfectly consistent with the rough and ready thing that I just showed you, because all these bells and whistles that are there are actually not that important numerically. So this is what Nordhaus found, and he first published this in sort of its full version in 1991 in Science. And essentially Nordhaus, and here you see younger, he's well into his 80s now. Here you see younger Nordhaus, roughly how he looked when he did this work. If the world were ruled by a benevolent dictator, what would she do? Right? That is the question that this model asked. So essentially we assume there's a philosopher queen, and the question is, how would she solve this problem? And the answer that you get is threefold. A little bit of emission reduction in the beginning, a little bit of deviation from the path in the beginning, a modest carbon tax in the beginning, then a higher carbon tax and more emission reduction later. The concentrations keep on going up. Now, this upsets an enormous amount of people, right? Absolutely hate this. A lot of people absolutely hate this kind of work. Nordhaus is good in the sense that he sort of stays above the fray, so very few people actively go after him, but people who have worked with him or who've repeated his analysis attract a lot of heat, including yours truly. I don't keep my head down, right? Nordhaus is much better at that. The first part of this conclusion is robust. It doesn't matter how you turn your analysis and how you parameterize your analysis, what sort of assumptions you make. You always want to start with a little bit of a carbon tax, a modest carbon tax. And the reason for that is very simple. That is that emissions in the short run are set in stone, right? The short-term elasticity is very low. So if you start with a big carbon tax, then essentially you're just imposing a cost on people without changing their behavior, right? So, and we talked about this also, about what is the optimal timing of emission reduction. This is essentially the same result. The first part, you always want to start modestly and then accelerate. The second part of the conclusions, how fast the carbon tax should go up, is actually greatly depends on all sorts of things. It depends on your discount rate, it depends on the decay rate of CO2 in the atmosphere, it depends on your scenario, how fast do emissions accelerate. It also depends on what you expect about future relative prices of renewables relative to fossil fuels. So essentially all studies, apart from one that is mistaken, say that you should start with a modest carbon tax and let it grow over time until you solve the problem, right? And there's only one exception, and that is a silly paper that says you should start with the carbon tax and let it fall over time. No. Everybody agrees that the carbon tax should go up, and people strongly disagree about how fast, right? But the part that really annoyed people is that you won't stabilize concentrations. And that goes back to basic cost-benefit analysis, right? What you want to do in a cost-benefit analysis is you want to equate the marginal cost of emission reduction with its marginal benefits. And then you find your optimal amount of emissions Q star. Now, how does that work? Well, this is our starting point, unregulated emissions. The first bit of emission reduction is cheap, right? 30% of energy is wasted, serves no useful purpose. We know how to add wind and solar to the power grid, right? The first bit is cheap, right? But as we push emissions further down, right, we first decarbonize the electricity sector, we roughly know how to do it. Then we're going to decarbonize transport. I'm not quite sure how to do that really, because electric vehicles don't really work. And that actually, if you're going to go for electric vehicles, then you need a lot more electricity on the grid. And where is that electricity going to come from? Perhaps not everything can come from wind and solar. And then we're going to decarbonize home heating, where there's really no good solution yet, not without essentially building everything new. I mean, heat pumps, electric heat pumps work well if you have a very well insulated house, but don't try it in your average English house, right? So that is becoming very, very difficult. And then actually the final bits of emission reduction are probably aviation, where we now have electric planes that can probably carry 2 or 3 people, not enough to carry 300 across the Atlantic, and space flight, where we just don't know how to do that without burning a lot of fossil fuels or emitting a lot of CO2. So first bits of emission reduction are cheap, final bits of emission reduction are very expensive, and that is just the way the problem is constructed. Now, what does the marginal benefit curve look like? Well, here we have unmitigated climate change. So the world may warm by 5 or 6 or 7 degrees, and that is pretty disastrous, right? We don't want to go there. But here the world is beginning, the world warms only by 3 or 4 degrees, and still there's impacts there and damages there, but not nearly as large as from 6 degrees or 7 degrees. And here we start pushing warming down to 2 degrees or 1 degree. And there may actually be net benefits of that, right? But let's assume that there's cost still. But if we drive emissions to zero, really, then what we're saying, well, we're bringing warming down relative to today, not from 6 to 5 degrees, where you can imagine a large benefit, but and not from 3 to 2 degrees, where you can assume some benefit, but from 0.1 degrees to 0, where it's actually, you can't actually measure that. That's actually a measurement uncertainty of the global mean surface air temperature. That doesn't bring any benefits, right? So the marginal benefits of removing the final emissions are very small. So the benefit cost diagram looks like this. And what you almost always find in a benefit cost diagram is that it's not optimal to have unmitigated emissions, but it's also not optimal to have zero emissions, right? And that is why Nordhaus finds an interior solution which has positive emissions, and then by the workings of the carbon cycle, positive emissions means that your CO2 concentrations continue to go up, and that means that your climate continues to change. Now there's one exception to this, or I should say a few more words. So everybody hated Nordhaus, right? And the reason that you win a Nobel Prize is because you start a new literature. So there's hundreds of papers trying to show him wrong, and they all fail. And the one exception, and that's actually an exception that Nordhaus himself put into DICE, but it actually goes back to Alan Mann. So much of Nordhaus's work goes back to Alan Mann, unless there is a so-called backstop technology. And what is a backstop technology and how does it change the picture? Well, a backstop technology is a carbon-free source of energy. We know that those things exist, right? So we have a source of energy that does not emit CO2. That's not a strange assumption. And you also need to assume that at some point that particular source of energy becomes competitive with fossil fuels. And at some point, with which I mean, if you impose a certain carbon tax, then it actually becomes competitive. Now, these are not strange assumptions, right? Run of the mill. The third assumption that you need to make about the backstop, and that is what makes it a backstop, is that it has an abundant supply. And the supply is so abundant that essentially your cost curve goes flat. And this is what that does to our cost-benefit diagram. Here you have your marginal cost curve again. The backstop is essentially, well, at this point, if your carbon tax is here, then your backstop will just take over, and from that point all your new energy will be carbon-free. And that can be here, it of course also can be here, and if it is lower than the carbon tax that you would want to impose, then you see indeed that your optimal emissions go from Q star to Q double star, right? And you see just this shift in action. That your cost curve goes flat is of course a strange assumption. The two biggest contenders at the moment are wind and solar power, and you can sort of say, well, yeah, the supply cost of wind turbines is flat, right? There's no reason to assume that if you order 10,000 wind turbines rather than 5,000 wind turbines that you would pay more or less per wind turbine. But at the same time, there's two issues here. One is that your wind resource is not constant, and presumably you put your wind turbines where the most wind is first, and that means that more wind turbines would be placed in climates with less wind and therefore be more costly or less effective in generating electricity. And the other issue is that, adding 10% of wind to your electricity system is relatively easy. The problem with wind is that it's non-dispatchable, right? You need to have backup power and frequency regulation and all that sort of stuff. That is relatively doable for 10% of your electricity supply coming from a non-dispatchable source. But if you go for 90%, you actually need a lot of, you need to work really, really hard to keep the lights on, right? So the assumption that the cost curve goes flat, that's a peculiar assumption. It's actually not the key assumption. The key assumption really of a backstop is that abundant supply, does not just compete at the margin but saturates the market. Now, if that happens, if your energy supply becomes carbon free, then your climate problem disappears, right? And with that, the justification for imposing a carbon tax disappears. But you then need to assume that your energy system or your economy is hysteretic, that is, it does not go back. So, no, wrong button. So you go here, and then actually this has to go to 0. The emissions go to 0. And why would you impose a carbon tax at this point, right? Your problem is solved. And presumably we want to do this at a reasonable warming. And that means that there's a lot of fossil fuels left in the ground. But there's no longer any justification for a carbon tax. So what is going to keep those fossil fuels in the ground, right? We know how to get it out. We know how to burn oil and coal and gas. We know where it is. And this is a very strong assumption, right? It's not just that at some point carbon-free energy will compete with fossil energy, and at some point all new investment will be carbon-free. But you also need to assume that once you have reached that point, the economy will never look back and return to fossil fuels. Now, if you're prepared to make those assumptions, and there's by now a whole bunch of people who are prepared to make those assumptions, then indeed your emissions will go to 0 and your climate will stabilize, and it's optimal to stabilize your climate. Okay, so far for part 1 and 2 for today. In week 11 we're gonna do away with the single benevolent queen, philosopher queen, and we're gonna have many philosopher queens who are running part of the world, and we're gonna look at the interactions between those, right? So that is postponed till week 11. After the break, we're going to talk about co-benefits and what that does to optimal climate policy. Okay. So I'm going to talk about co-benefits or secondary benefits or ancillary benefits. They're all the same thing of climate policy. And the motivation goes back to this particular cartoon, which is also almost 30 years old, by Joel Patton, published in USA Today, which was once a very big newspaper. And one of the reasons that climate policy is not going quite as people had hoped or imagined it would go is it's probably good, so you always hope that somebody else would reduce their emissions before you do, and climate is something vague, and it's in the future and it's in faraway countries, so why should we care, right? So for those reasons climate policy is not going as it should, and what people have argued, and that is shown here, is that you actually want to reduce emissions for other reasons. You want to reduce greenhouse gas emissions for other reasons. You want to focus on energy independence, you want to preserve rainforests, sustainability, you want to create green jobs, livable cities, clean water, air, healthy children, and so on and so forth. And that list here is of course put up in response to this middle-aged white guy standing up at what seems to be a climate summit and saying, well, what if climate change is not a problem at all? What if it's a big hoax perpetrated by the Chinese, and we would create a better world for nothing, right? And then the speaker points at this list. At the moment, of course, energy independence is again at the top of the list. And that seems to be behind another push for renewable energy at the moment, but 6 months ago it was all about creating green jobs, right? President Biden says we want to do the Build Back Better plan, which reduces greenhouse gas emissions in order to create green jobs. Frans Timmermans of the European Union, who is in charge of European Union climate policy, says we want to do this because it creates green jobs. And also Boris Johnson says exactly the same thing, right? We don't want to reduce emissions because we care about climate. No, we're gonna claim, or rather pretend, that this is gonna create green jobs, right? And now, since the last 3 weeks, the claim is we're going to reduce greenhouse gas emissions because we don't want to depend on energy imports from Russia, right? And the question is, how strong are these arguments, and are these arguments at all, right? These are the co-benefits of climate policy. The things, if you do climate policy, you get for free. I'm going to focus on air pollution because when I prepared this, that was the main thing. And it's actually easier than green jobs, which was the other main thing. And energy independence is a really complicated issue. So you don't want to see the math of that. So I'm going to, this is relatively new. So it is how I do things, that is in calculus rather than graphically, but there will be some graphs as well. So we're going to assume that there's two types of emissions that we care about, G and A, and rather than look at emissions, we're going to look at emission reductions, and the G refers to climate change, greenhouse gases, and the A refers to air pollution. The benefits of emission reduction is this function here. It's the B for the benefit, and then that depends on how much we do of A and how much we do of G, and that then comes with their respective parameters alpha and I think it's XC, but I should have looked up my Greek alphabet. Now these two problems interact with one another. If you reduce your greenhouse gases, if you reduce your greenhouse gases by R, you're also gonna affect, if you reduce your greenhouse gases, and that's your effort is denoted by R, you're gonna affect your greenhouse gases, but you're also gonna affect your air pollution via this term here, right? And if you're gonna reduce your air pollution by S, you affect air pollution, but you're also gonna affect greenhouse gases through this channel with the pi that you see there, right? So the two problems interact with each other. Cost of emission reduction are a quadratic form. The more you do in greenhouse gas emission reduction, the higher your cost. The more you do in air pollution reduction, the higher your costs, right? And that's a quadratic form. This is linear, so this is an LQ model, linear quadratic. And the good thing about quadratic terms is that then your first order conditions are linear. So you have a explicit solution, right? An analytic solution. Now, the benefit function is given here. We know what A and G are, so we can substitute that in to get this expression. And then we can sort of gather the S's and the R's to get this, what looks like an unwieldy expression, right? So the benefit of greenhouse gas emission reduction equals rho. So that is how much our emission reduction reduces emissions, times chi, and chi is how much we care about our emissions, and the effect of our greenhouse gas emissions, tau on air pollution, times how much we care about air pollution, alpha, right? So this makes intuitive sense. So copy this equation to the next slide. It's the same thing there. This equation you looked at before as well, the cost of emission reduction. So the optimal emission control for greenhouse gases R is cost-benefit analysis, marginal benefit should equal marginal costs. Marginal cost, that's why the half is there, is lambda r. Marginal benefits, very simple. I mean, it's an awkward equation, but it is linear, right? So that is alpha tau plus chi rho. And that means that our optimal emission reduction, R prime, is this term divided by lambda, so that is chi rho over lambda plus alpha tau over lambda. Or in words, the optimal control for R, for greenhouse gases, equals our concern about climate change times the effect of climate policy on emissions divided by the unit cost of climate policy, plus our concern about air pollution times the effect of climate policy on air pollution, alpha times tau, and again divided by the unit cost of climate policy, right? And graphically that looks as follows. The brown curve here is the marginal cost of greenhouse gas emission reduction, right? And the more we reduce, the greater the cost, and we assume this cost curve to be quadratic, so the marginal cost curve is strictly linear, as you see here. Then in a cost-benefit analysis, we want to set this equal to the benefit, right? And we assume that this was actually a linear function, so the marginal benefit function is constant. It's like this, it's a flat curve. So this is what we want to do in a cost-benefit analysis, marginal cost equal to marginal benefits. But there's two benefits, right? There's the primary benefit of avoiding climate change, and there's the secondary benefit of doing things with your air pollution. And that's the purplish curve that you see here. Now, if this is a benefit, then you would simply add that, right? You would simply add that particular benefit to arrive at this point. But we did not make any assumptions on the sign of this. If it's actually not a benefit but a loss, then of course you would end up here, right? So that is how it looks. Yeah. And the crucial question is this tau? I mean, the alpha is pretty clear, right? This is how much we care about air pollution. Air pollution is bad for you. Unless you happen to be a tree, but I assume that you guys are not trees. So this alpha is, the sign is clear. This tau, actually not at all clear what the sign of tau would be. So how can you reduce greenhouse gas emissions? Well, one thing you can do is you can switch from coal to gas, which reduces CO2 emissions. And we looked at that, I think, in week 3, where I showed this picture for the United States, where exactly that is what they did when they switched from coal to shale gas. Good thing about gas is that it burns much more efficiently and therefore reduces or emits much less CO2 per joule of electricity generated. But gas also comes in a much purer form, whereas coal always comes with contaminants, and particularly sulfur and other things, and therefore it doesn't burn as well, and it emits sulfur dioxide and what have you. So if you switch from coal to gas, you're going to reduce your CO2 emissions and you're going to reduce your air pollution. So in this case, tau is positive and you want to work harder on greenhouse gas emission reduction. But there's another way of reducing CO2 emissions, and that was popular in Europe for a very long time, and that is to switch from a petrol car to a diesel car. And a good thing about diesel is that the engine is much more efficient. So you get much more kilometers, much more mileage out of a tank of diesel than you get out of a tank of petrol. And therefore, per kilometer driven, you emit less CO2. However, now so that is what Europe did for a long time. Heavily focus on diesel engines. And one of the reasons that we did that is because we believed that the new diesel engines were clean and burned cleanly. And then in 2000, and I forget which year it was.
2008, 12.
Yeah, you guys were teenagers. Not that long ago. We discovered that these tests had all been falsified, right? And that actually diesel engines emitted a lot of particulates. And those particulates did a lot of damage to air pollution and to human health and to nature. And in this case, your tau is negative, right? Your attempt to reduce greenhouse gases, to reduce CO2 emissions, actually increases CO2 emissions, increases air pollution. And this came out recently in the news. Other people have known this for years. Wood burning, you burn wood rather than oil or coal or gas to heat your home, you emit less CO2 because it's a recently grown tree rather than a fossil plant material. This came out in January of this year, that wood burning at home to reduce CO2 emissions and keep your energy costs down, wood is quite expensive, is now the biggest cause of particle pollution in the UK. No, this was December. And then in January, this study came out, and this is in Athens, where those wood burners now seem to cause half of the cancer that is associated with urban air pollution. So yeah, you cut your CO2, but you did not at the same time cut your air pollution. You actually make your air pollution worse, right? So there is no a priori reason to assume that this tau is positive, or this tau is positive, right? Your secondary benefit may be a secondary loss. Now, I started with this guy standing up at this conference and claiming that climate change is a hoax. Climate doesn't change, we don't need to care about this. Then your chi is 0, right? This term cancels. But your greenhouse gas emission reduction then does not go to 0, right? Depending on whether your tau is positive or negative, you still want to do something about your greenhouse gases, right? So that is true for R. The same is true for air pollution. For S, the model is set up completely symmetrically. So you have the same things here. Now the question is about your pi. What is the effect of air pollution control on greenhouse gases, and that can be positive or negative. Again, if you switch from coal to gas, if you do that for reasons of air pollution, as they're currently doing in China and India, then you're also going to cut your CO2 emissions, so that is good. But the way we solved our air pollution problems reduced our air pollution problem in Europe and North America and Japan is by putting scrubbers on smokestacks. Essentially removing the sulfur from the flue gas before it enters the atmosphere. Now that really, and then the same can be done with nitrogen, that really works, but it's also really expensive because you need to build a scrubber plant. It's going to set you back tens, if not hundreds of millions of pounds. But it also takes a lot of energy. And typically about a quarter to a third of the energy of a coal-fired power plant is diverted to the scrubber in order to make sure that the nitrogen and the sulfur does not enter the atmosphere. And that of course means that in order to deliver the same amount of electricity to the grid, you need to burn more coal and emit more CO2, right? So that is completely symmetric, and again it depends on the sign, in this case of pi. It can be positive or negative. So greenhouse is intermediate conclusion. If greenhouse gas emission reduction helps to solve other problems, then we should do more of it. But if it makes those other problems worse, then we should do less of it. Now this is true for a linear model. Let's make the model less than linear. And the derivation is exactly the same as it was apart from the red bits. So the benefits of emission reduction are as they were before. Emission controls are the same as they were before, but I'm going to fiddle around with what is happening with air pollution, where I'm going to assume that rather than have this tau, where our efforts to reduce greenhouse gas emissions affect our air pollution, I'm going to assume that the effect of that effort depends on our air pollution policy S. And this is one way of writing it. This is perhaps a clearer way of writing it. This tau that you see previously was the effect of greenhouse gas emission control on air pollution. Now I'm going to say, well, this tau is going to be smaller if I work harder on air pollution. Right? So the way to think about this, if you switch from coal to gas, you reduce greenhouse gas emissions and air pollution. But if you have already scrubbers on your smokestacks that take out the sulfur and the nitrogen, then there's very little air pollution left. And therefore, yeah, you can switch then to coal, from coal to gas, but if the coal was already relatively clean, then it has little effect on air pollution, right? So that is what this term here captures. That the harder you work on S, the less the effect of greenhouse gas, less the effect of R would be, right? So a very simple variant on the model, right? So the cost of emission reduction are the same. We're going to rework the benefits again, and we find the same thing here, and now we have this particular term pop up here, right? Copy that to the next slide. Optimal control for R is still marginal costs equal marginal cost equal marginal benefits. Marginal costs are as they were, lambda R. Marginal benefits are as they were, alpha tau plus chi rho. And now we have the alpha, this is still how much we care about air pollution, and the psi pops up there as well. And see, we have psi rs, and we do the derivation to R, we are left with psi s, but this is an effect on air pollution, so we an effect on air pollution, so we should have an alpha in front. This term pops up as well, right? So this is what we had previously. Minus this term, we can then solve for the optimal R, and this should have been a prime here. No, this should not be a prime here. We can solve this or rewrite this as this particular term, right? Where now our co-benefit falls if we work harder on S. Now it's a completely symmetric problem, so the same thing pops up in S. And naively, you can think of it like this. So this is the primary benefit. This is what we had previously, the marginal, the co-benefit, right, the secondary benefit, but now only for S is 0, if there's no air pollution policy. But then if we do air pollution policy, then that benefit will fall. So rather than having this dark green line, we fall a little bit down. Right? So that is your primary signal. But there is a problem with this equation, where your R depends on your S, and your S depends on your R, right? So this is not a solution. This is just rewriting the equation. Now, this is a system of two linear equations with two variables, so we can solve this. And you really want to know how to do that, right? And if you do so, then this particular thing pops up. This is the optimal solution for R. It still depends on alpha tau chi rho. We have a kappa here and a kappa here, so those two cancel, right? And we still have this particular term. Right, so we're still subtracting stuff. So that is what we're just looking at. But the real main difference is that now the slope of this curve, we also need to subtract this particular term. And on the slides that I make available, I actually do the derivation of this. I don't feel like doing it now, and you guys don't look particularly excited about seeing this bit. The effect of all this is essentially that your curve becomes less steep. So primary benefit, secondary benefit if no air pollution policy, secondary benefit with air pollution policy. And then the other effect is that the marginal cost curve is less steep. It flattens and you move slightly out. So that is what is going on if you have this interaction. So to sum up, and then we're done. I actually did it in 20 minutes. No, it's 15 minutes even. If greenhouse gas emission reduction helps to solve other problems, then we should do more of it. But it's not necessarily the case that these benefits are benefits. And the second thing that you need to keep in mind is that these, if they are secondary benefits, then they actually shrink with policies that are directly aimed at these problems. And a final remark that you can make about this, if you are so concerned about air pollution, don't you think that greenhouse gas emission reduction is a clumsy way of reducing your air pollution? Don't you think there is a smarter way of going directly after air pollution? Or if you want to create jobs for people, do you think that greenhouse gas emission reduction is a good way of creating jobs, or are there not other policies that would create jobs, right? And so on and so forth. If you worry about energy dependence, are there not smarter ways of reducing your energy dependence? So yes, the secondary benefits are real and they do affect your policy, but it is of course never can be the main reason to do something. You can never say we're going to solve climate problems. We're going to solve the climate problem because we care about employment. You want to solve the climate problem because you care about the climate problem. If you care about employment, which you should, then you should have a proper employment policy. That's all for today.